Hi, this is TheoryStation, and I'm John Duggan. The program is Rational Choice Modeling, and the series we're in is the Basic Formal Theory Toolkit. This is the fourth installment of the series. In the previous installment, I talked about cost-benefit analysis, and what I want to do in this installment is switch to a more political science kind of model, and I'll call it the one-dimensional policy choice model. Okay, so the title sort of says it all, I guess. But let me fill it in. So I want to think about a politician who has to choose a policy. I'm not going to model the politician explicitly because that's kind of, just assumed. The first thing I want to describe is the set of conceivable choices that this person could be making, and it's going to be one-dimensional. Okay, so it's going to be, I'm going to think about these choices as belonging to the real line, and I'm actually going to suppose that they are an interval going from -1 to 1, and I'm going to call this a policy space, but it really is just the set of conceivable choices this politician could make. Graphically, this is the real line, then it's going to include -1 and 1 and everything between them. It's really not critical for the model that that this be an interval. It could be the entire real line, or if you want it to be an interval, it could go from 0 to 1 instead of -1 to 1. These are just modeling choices and don't really affect too much, if anything. So that's our policy space. Now, again, we're in this rational choice framework, so we need to describe the preferences of the decision maker. And, I can't write down a ranking of policies as a list because the policy space is infinite, right? This interval from -1 to 1 has a continuum of different possible choices. So I'm going to use a utility function. But first let me tell you what the preferences are going to be. So I'm going to assume that the politician has some ideal point. I'm going to call that P. Now what an ideal point is it's policy. It's going to be in this policy space. It's going to be a policy that's better than anything else for the politician. Okay? And okay, that only tells you what this guy's favorite policy is. What about other policies? Well, I'm going to keep things really simple here, and I'm going to assume that this guy wants his ideal point. That's the best thing he can get. And then for any other policies, he just wants policies closer to the ideal point. Okay, so if I put, suppose I put P right here, and then I choose, let's say, a policy X like this, and then a policy Y like this. If I compare the distance to the ideal point, you can see that X is further away from P than Y is. I'm going to assume this guy just likes things closer to his ideal point. So in this case, he's going to prefer Y to X. Of course, that's just two particular choices there, but that's just the general rule. If you take any two policies, the one that's closer to P is going to be better. All right, so that assumption is called Euclidean Preferences. And the reason for that really doesn't become more apparent until more general models, but that's just the terminology that we're going to use. In terms of a utility function, one possibility would be to define utility as follows. So for any policy x, we have to assign a number to it. Let's look at p minus x squared, but I'm going to multiply it by -1. So think about how this utility function works, right? We plug in a policy x, it has to give us a number, and the rule for utility functions is that it has to assign higher numbers to better alternatives. All right, so if we plug in a p for x, the utility is going to be p minus p squared times -1. Well, p minus p is 0, so if we plug in a p, the utility from that ideal policy is 0. What if we plug in something that's further away from p? Well, like an x, then if it's further away from p, then p minus x squared is going to get bigger, but we're multiplying by -1, so that means the utility goes down. So if we were going to graph this, if this is p here, then the utility function is going to have this shape here. Okay. And you can see that alternatives that are further from p are going to have lower utility. That's all we need, right? We assign lower utility to things that are worse, higher utility to things that are better. This is called quadratic utility. Okay. Notice that that's not the only utility function that we could use. I mean, we could also just simply take the absolute value of p minus x. That's just literally the distance between p and x. Multiply that by -1. That gives us another utility function that has this shape. Right? So it's technically a different function, but it has the same feature. The alternative or the policy with the highest utility is still p. It's the ideal point. And if you look at alternatives that are further away from p, they have lower utility. So, I mean, we could use either utility function. In fact, I mean, there's infinitely many we could use. So, you know, I usually stick with the quadratic, but it's really a matter of preference. All right, so that is, those are the basic constituents of the model, and we're going to impose this optimality principle. And so what is this guy going to choose? This is pretty trivial. If you have a unique favorite policy and that's available to you, well, you're just going to choose that policy, right? You're going to choose P. So, you know, that's not a super interesting model. However, it's one of those building blocks that we use, and you know, this is a model that's been used in so many different ways and built on. This is just the absolute most basic version of it. Okay, so let's not stop there. Let's push this a little bit more. If we, you know, one thing we could do is suppose that there is a feasible set of policies. This is something that we did in the basic preference and choice model. Okay, so that's going to be a subset of the policy space that's actually available to the decision maker. Well, in this setting, we have the structure of the real line. So I'm just going to go ahead and assume that this is an interval. And that bracket notation means that the feasible set is everything from policy A to policy B, including A and B. So let's go back to our real line. If this is -1 and that's 1, suppose that A and B are like so, then the feasible set would be everything between A and B, including those two. All right, so the optimality principle would say that this politician chooses the best policy they can that's available to them. And now if we look at this, it's still pretty easy to work with this model. Clearly, but now the form of the policy choice is going to depend on where the politician's ideal point is. If P is in that policy, in that set of feasible policies, no problem. The politician just chooses his ideal point, and that's all there is. Suppose, though, that P is outside that set of feasible policies. Now the politician can't choose their ideal point. It's not available to them. So they have to choose the best thing that they can. With this structure, the politician, remember, likes policies as close as possible to their ideal point. And here, obviously, for a politician whose ideal point is to the right of the feasible set, they're just going to choose B, the right-hand endpoint of the feasible set. That's the closest thing they can choose to their ideal point. On the other hand, if they were to the left of the feasible set, they would choose A. Okay? We can graph this. What I'm going to do now is I'm going to graph the optimal policy choice as a function of the ideal point of the politician. Okay, so this is the Cartesian plane, and so each dimension is going to represent policies. Let me put in our interval -1 to 1. And let me put in this 45-degree line here. And finally, I'll put in our feasible set. This is A and B. All right, so I'll use blue for the optimal policy choice function. Now, if P is in that feasible set, the politician just chooses their ideal point. So if this is P, then I'm going to use the vertical axis to denote policy choices. So if your ideal point's P, what policy choice are you going to choose? You're going to choose your ideal point, which is P. And basically, we're just going to go up to the 45-degree line and go over to P. If, on the other hand, your ideal point were over here to the left, well, you're just going to choose it again. So we go down, and again, your policy choice is just your ideal point. That's true anywhere in this interval. And so the optimal policy choice as a function of ideal point is going to be just, the graph that's going to be the 45-degree line. I gotta go up to here. And all right, now suppose P is to the right of B. As we just said, well, then the politician is going to choose that right-hand endpoint. They're going to just choose B, and that's true anywhere in here. And to the left of that feasible set, the politician is going to choose just A. And that's true everywhere to the left. And so the optimal policy choice function is this heavy blue sort of piecewise linear function here. So this is the optimal. All right. So so again, here I'm using the horizontal for ideal points, right? So as a function of the politician's ideal point, we can now see what the optimal policy choice is. This again actually is a comparative statics exercise. We're varying the ideal point and then seeing how that affects the optimal choice. Okay, so this is kind of an abstract exercise. There's a question, you know, why are we thinking about this, and where does this feasible set come from? Well, there's different stories for that. One could be just that there's some, you know, technological constraints. But in the next installment, I want to talk about, suppose that politics is a little bit more complicated than just choosing a policy. That suppose that a politician has to interact with another politician or a voter in order to enact policy. And we're going to see that you can, you know, in a more complicated model of politics, you can get something that looks like this, where there's a feasible set, and you know, this might seem pretty abstract, but we'll get it out of a, I think, a more interesting model. All right, so that's coming up in the next installment.